Hello team! Welcome to another video guide, this time for PA3 the Parser using OCaml and ocamlyacc. We're going to cover how to deserialize the PA2 CLX file in OCaml and store it as a queue of tokens. That'll be fun. And then we will feed those PA2 tokens in to serve as a lexer for our new PA3 OCaml parser. We'll have to represent the AST, which we will do using algebraic data types or abstract data types. And then we're going to define the parser via grammar rules, including line numbers and some error handling. At the end, we will serialize the AST, and there'll be a bit of a live submission demo to see how things go. All right, let us get started. So we've read the PA3 the parser description, and once again, we need to name our file something specific. I'm going to name it main for now. MLY, Y for yak, is the special extension we use for ocamlyacc files. Oh, but I really don't remember how to use ocamlyacc files. Maybe there's some sort of like ocamlyacc manual. Oh, this sounds awesome. All right. Overview, syntax of lexers. Hey, this sounds familiar. Where have I seen this before? But this time I want something... here we go, a complete example. I love these desk calculators. We're sort of, no, not that. Oh my gosh, this, yes, love it. Everyone is sort of required to have one. So we will get started with this. Oh man, how many times do I need to move that over to make it line up? Pretty close. All right, so this is Wes Weimer, WRW6Y, PA3 Parser for cool. You notice my syntax highlighting doesn't seem to quite know MLY files, but we will survive. And then we want to take a look at some of these parts. Up here at the top, we get the chance to list all of the token types that we're concerned with. And this optional argument, this int in brackets, is the lexeme, or the information the lexer is going to give to us. One of the things we'll want to track everywhere is line numbers. I could represent line numbers as integers, but I will be lazy and represent line numbers as strings. And this is because we never need to add them. We just carry them around and print them out. All right? So every token is going to have a string associated with it that's going to be its location. So things like class or L_paren or R_paren, those are some of the tokens we care about. But there might also be tokens like integer that would have some other information associated with them, the lexeme. And once again, we could use int for integer, but I will be lazy and use strings for every lexeme, because once again, we never have to manipulate the lexemes at this point. Right? We just have to print them out. So I'm just going to use strings for everything because, heck, if we're going to use OCaml, why take advantage of its strong type system? No, wait, anyway. But that allows us to handle integer and string and identifier and type fairly similarly. We will want some special end-of-file token that may or may not have some lexeme information associated with us. Oh, and now here we can see some precedence information. And maybe we'll want plus and times, but I'm not going to do minus or divide yet. Oh, unary minus, non-associative precedence. Time for another day. And now, one of the next things we have to do is indicate which of our grammar rules is the starting point. Right? So in the class examples, this is often named something like S. We'll call this something like a cool program. And we have to indicate what type we're going to get out when we're done parsing. Conceptually, for me, a cool program is a list of classes. How did I know that? I don't know. Let us go back to the cool reference manual, and we'll see what we can do to find cool syntax. And we just see here at the top, a cool program is a non-empty list of cool classes. I'm actually going to be lazy and allow it to be empty, but it's a bunch of classes separated by a semicolon. So we can see how these rules in ocamlyacc, they look a bit like what we'd write in class. If in class we'd say something like e goes to e or int, then the rule in ocamlyacc would be something like, like this. And we're going to have a convention of using uppercase things for tokens, following what we saw up here. Convention, uppercase is token or terminal, lowercase is non-terminal. Right. So a cool program is just a class list, and then you write some code over here. And in this code, the first thing on the left of the colon is $0, and this thing is $1. And right now, we're just going to return $1. And that's not so obvious yet, but it'll be a little clearer when we get to some other examples. And, well, so what's a class list then? It's sort of like we're making a promise that we have to fill out later. Well, for every list, there are two options. Either you can have nothing, or you could have conceptually a class followed by another class list. This is a way of writing in grammars, 0 or more of these. Oh, but I noticed my syntax highlighter is getting mad at class, and probably someone somewhere is going to care if we use the word class, so we'll use cool class or cool type whenever that becomes an issue, just to prevent things from yelling at us. So if you do nothing, that's the empty list, but if you do something, that would be, I just build up a list here using the cons operator. Oh, but actually every class ends with a semicolon, so we'll do something like that. You don't need to tab this stuff over. This isn't Python, but we're just going to do it for fun. Oh, I've mentioned this semicolon token. You better put it up here. All right. So cool program is a class list followed by the end of file marker. And then what's in a cool class? We'll just write out a few of these rules, and then we'll sort of fill in the rest of the types later. Not quite right. Here we go. It's got a class and then a type, and we'll do no inherits for now, and then some braces, and then a semicolon. So you've got the word class, and then you've got a type, and then I've already forgotten. And then you've got an L brace, and then you have a feature list, and then you have an R brace. And we don't need the semicolon here because we've got it on this line. All right. There's another option for class which involves inherits, right? But I'm a little too, I haven't done that one quite yet. And when we see one of these, well, now is when we need to start thinking about our abstract syntax tree, or how we're going to represent these. And I'm going to use a type I haven't made. This would be some sort of class with no inheritance. And I'll need to note its name, which is thing2. Remember, 0, 1, 2. And I'll also need to know its list of features. All right. So now, almost done. We need some way of defining a feature list. This is a recurring theme in PA3. Any list is either nothing or, and now you get a chance to see where that weird semicolon rule came from when we were defining Cool's grammar. It's because it makes it so easy to write these. So easy, easy-tastic. All right. So now I need to know what a feature is, and we're only going to consider one of them for now. And the feature is either a function, oh, too complicated for me, or an attribute with an optional initializer. Oh, initializer, much too complicated for me. So how about we just have, you can have an identifier, and then a colon, and then a type. And if you do this, you get an attribute with no initializer, like so. And this grammar, cool program, depends on class list depends on cool class and class list. Here's cool class, depends on feature list depends on feature. Here we are with feature. This is sort of a reasonable self-contained grammar, and this is where we're going to do a lot of our testing. If, for example, we should totally be able to parse a cool file like that. All right. Now this is not a valid cool program, like it doesn't have main in it, but we could at least parse it for programming assignment 3. So this is the sort of thing we want to get to eventually. Here was the word class, here was a type name or an identifier, and then we had all of these down here. And we'll have to double check to make sure later on that we're using type and identifier correctly and all of that jazz. All right, so there's the test case that we want. They had some other stuff for dealing with expressions. We will bring that back in later. And now we want to see what else we need in one of these. The definitions for the corresponding lexer. Here is the main program. All right. Now it turns out that once again, we're going to be able to put everything we want to do in a sort of a single ocamlyacc file. Let's go see if we can find the place where they talk about the format. All right, here we go. So we've got some sort of header and then declarations and then rules and then a trailer. So you'll notice this weird like double % thing. That actually matters. And I can put any code I want, any OCaml code I want down here. And in all of my OCaml programs, I start out the same way. Because now I never have to remember how the double semicolon thing works. So this main will get called at the end if everything worked out. Hello world, we got here. We're not actually going to do any parsing. We're just going to see if this even compiles, because that's at least half the battle with OCaml. Right. And potentially, let's just go check out this format. We also have a header at the top. Notice this bit. Comments are enclosed as in C in the declarations and rules section, but in the header and trailer section. All right. So we can also have, I can't write any OCaml code at the top here. And I'll even move my little commentary. All right. So now I made up these things like attribute no init and class no inherits. And I need to start filling in data types for them. Right? So a cool class, well, right now there's only class no inherits, but eventually we'll have class inherits of, and then each one of these has an identifier or a type, and then a feature list. Right. So we will have our identifier. Which for us, you'd think is normally just a string, but remember, we're going to track the line number plus the actual string lexeme. Line number could be an int, but I'm so cheap that I'm going to make it a string. All right, so we've got the class name, and then we've got a feature list. And we don't need them, but I'll put parentheses here just so that there's no potential confusion. And I can use and when I want to link up a bunch of types together. And a cool feature, the one we have, cool feature? No, all the jokes are that bad. Did I call it atter or attribute? I wrote out attribute. Oh, that sounds like a mistake. An attribute without an initializer. And this was officially, where was it down here? An identifier and a type, but by the time we get to parsing, after we've built the abstract syntax tree, identifiers and types look very, very similar. So I'll just be using identifier for both of them. We'll see in a bit that they print out the same way. This is just going to save us a bit of time. So then a cool program is a cool class list. And now we had this fix me. When we parse main, our main is a cool program. We get out something of type cool program. Just to make this super clear, this is our cool program grammar rule. And this is its type, the cool program type. All right. So we're getting close to the time when we would actually want to pass this through ocamlyacc to make an ML program and see if it works. Let's go see how that goes. All right. Symbol L brace is undefined. You know, you're probably right. We had L paren and R paren, but let's do braces instead. Symbol identifier is undefined. Yeah, you didn't see that. All right. Symbol colon is undefined. Sure. How am I choosing which one of these lines to go on? It's only the things down here that carry along this extra lexeme. For all of these, like colon or semicolon or times, I only need to keep track of their line number. All right. So now if we look in this directory, that actually produced these files main.ml and main.mli. We actually don't need this mli file yet. So we could just take a look at main.ml. Let's actually pull it up. You notice at the top it's got all of these tokens. It took everything we wrote on these lines, lines 28 and 29, and it automatically spit out a type for them. And then down here, way at the top, you can see, oh, here are the comments I put in. And it says what an identifier is in the cool class and blah, blah, blah. And now this is just a bunch of tables, right? It's encoding a push-down automaton, blah, blah, blah. But way at the bottom, I've jumped to the end of this file. You can see the code I wrote in the footer. Right? Hello world. So let's see if we can actually compile this. Syntax error, main.ml on line 10. Oh, in this token of string cross string, right, let's just go see. Main.ml, line 10, characters 2 to 3. So, where I have this comma, that's not actually correct. When we're talking about types in OCaml, you use the star to indicate a tuple, and when you're building a tuple or a pair, you use the comma. So I mistakenly used the expression syntax instead of the type syntax because I am not very good at functional programming. Now notice, every time I make a change, I have to rebuild this and try again. Now we got down to line 12. Where was it actually complaining? In main.mly, notice the difference here. Main.mly line 12, we don't know anything about identifiers. So here is line 12, feature is identifier. Did I spell it correctly? No. Oh my gosh. I can't spell in English. And now at this point, I'm getting tired of writing ocamlyacc all the time. So I'm going to make what's known as a Makefile. And my program is called main, and it depends on, by the way, if you don't know how to make Makefiles, don't worry about it or post something on the forum. It's not something we cover explicitly in class, but it can help out. To make main.ml, we run ocamlyacc on main.mly. And then to eventually make main, we need main.ml. And what we're going to do is remove main.mli. Just make sure that we have tabs because Makefiles require them. And then we'll try to compile it. And then whenever we want to make clean, we can remove main.mli and main.ml and also .main. And just for, I'm running this under Windows, we'll just make it super clear. We'll call this main.exe. All right, so I should be able to do make clean. Cannot remove all of these things. When you're going to remove a bunch of things in a Makefile, the -f flag, F for force, is sometimes handy because then it doesn't yell at you. And now I can just say make, oh, and it runs all of the commands I wanted. And look, this time it totally worked. We ended up with main.exe. And when we run this, we're going to see hello world because we didn't actually do any parsing. More on that story later. All right, so we have our basic grammar, but we're going to need to start putting in these tokens. Where do we read them? Well, we need to read in the tokens from the PA2 CLX file. So the token file name is given on the command line as sysargv1, and we will use OCaml's approach to open in files. And where do we want to store all the results? We could store them in a list, but actually we're going to, because of the way the parser calls us to get tokens, it's actually very hard to write this in a purely functional manner. So we might as well use one of OCaml's many imperative data structures. We'll use the queue. All right. And there's a way to create a queue, and notice in-place modification. All right. I like that, kind of like the OCaml hash table. All right. So Now I could do all of this right here, but maybe I'll be super nice and make a little helper function. Right? We'll read in tokens, and in fact, we do all of this together. When we're done, we'll close in fin, and we will let our tokens be one of these new queues. And then our standard approach for reading an input in OCaml is just to go on forever until there's some sort of exception. We want to get the next line. And for us, that's normally something like input line from fin, but this might actually be spelled read line, and I never actually quite remember which one it is. We'll see how that goes. But there's another trick to this. Notice that often the OCaml documentation is stored with your OCaml installation, so if you can't be bothered to go to your web browser, you can find it here. We want to write cross-platform compatible code, like not have to worry about this carriage return stuff. So whenever we read one of these lines, we'll call string.trim on it, just in case. And then what happens? Well, what do these PA2 token file formats look like? You remember from the previous assignment, but we can also ask the reference lexer to make one of them. So we see that everything is a line number followed by the token type. So the first thing we do is the line number is read a line, and then the token type is the get a line. And what I'm going to do is have a big match statement. So if they said class, then which one of these tokens does it correspond to? Well, it corresponds to the class token. But remember, we said that every token took a string. So we'd have to put in the line number. And indeed, I'm going to be super lazy and just call that L, because I'm going to have to write it out every time. So if they say semi, then that's a semicolon. And if they say colon, then that's a colon. And if they say L brace, that's an L brace. And if they say R brace, that's an R brace. And if they say, I'm forgetting what some of the other ones are, plus times, great. If they say plus, that's a plus. And if they say times, that's a times. But there are a few things they can say that require a little more work. If they say integer, well, that's an integer and it lives on line L, but we also need to get the integer value. Right? This is the lexeme. And if they say string, and if they say identifier, did I spell it correctly this time? And if they say type. And we'll come back to this. What we're doing is deserializing, reading in this format and turning it into our favorite data type. If it's anything else, then print out, oh no, unexpected token type, and exit the program. All right. So this match token type, it's returning conceptually. So this is like, let the actual token be this. We match every let with an in. Once we have the token, we can just add it to the queue. Oh man, what order how do we add? Okay, so it's add X to queue. So we add the token to our tokens queue. And I'll just up the name for this for extra readability. Tokens queue. And then when we're finally done with this, we just return the tokens queue. Seems pretty good. All right. However, as we're reading this in, just for convenience, we're going to want to track line numbers in a bunch of different places. We have them embedded in all of these uppercase tokens, which is very good for the parser. But reading ahead, I am also going to store the line number in the tokens queue again. Gratuitous extra line number, because that may help us with parsing errors. More on that story in a bit. So if that's the token file name, then I'd have the tokens queue, and I get that by reading the tokens from the tokens file name. And then I'd do something with it, like use it to parse. But maybe for now, oh, we can get its length. Let me just print out hello world. Number of tokens is... And let's just see if this even compiles, right? Does this pass the OCaml type checker? Because probably it will not. How do we check that? If we wrote our Makefile correctly, we can just rerun make. Aha, on line 95, tokens file name, did you mean token file name? Yeah, probably. All right. Rerun make. Oh, and it works. All right. So let's say we run main on test clx. And it says there are 13 tokens. I mean, that's probably correct. The file is about 31 lines long, but some of them are identifiers or strings. I mean, that seems pretty good as a sanity check. We could make a better one. Here is something that should have 2 tokens. And it says there are 2 tokens. All right, I like that quite a bit. So I've gained confidence that we're reading in the tokens correctly. And now it is time to call our parser. Okay. And just like in the Python version, if you've seen that video, ocamlyacc is expecting us to pass in, or it's expecting us to use this sort of thing, one of these lexbuff maneuvers. And then you call the parser and you pass in this token getting function and the lexbuff. Right? So let's just make a little copy of this because we are going to need this to do our parsing. All right? This is going to be our parsing. So the first thing we need is some sort of lexbuff. Normally this is some sort of string like class point inherits io blah blah blah. This is what we'd read in from the file, but we already did that in PA2. So we actually don't need a lexbuff because we're just going to pull our tokens out of this tokens queue. We're not going to do any lexing. You already did the lexing in PA2. No new lexing here. So we want to make the world's fakest lexbuff, and it turns out that there is a way. You can just make a lexbuff from a string, and we're going to make an empty one. Because no one is ever going to read it. So we're halfway there. We've got the lexbuff, but now we need this lexer token function. All right? And this is a function that takes in the lexbuff and decides what to do. And what we're going to do is take a look at our tokens queue and return the next one. So if our tokens queue is empty, then we've reached the end of the user input and we will return the special end of file token. In all other cases, we can take something from the top of the queue. And remember, we stored the line number here for no adequately explained reason. But how do we get something from a queue? Is it queue.get? Man, I do not know. Let's just pull that up. Take, sure. Removes, right, all right. So we take this from our tokens queue. Right? Recall, destructive imperative update. Curse UVI. All right. And then what we want to do is return the next token. Eventually, we're going to want to do something with this line number, like when we have to do error reporting. But for now, not so much. So then this stuff here, this is fake up a lexer using our queue of PA2 tokens. This is how we're going to do it. And this means that we should now be able to call, right? Well, ours wasn't called main. Ours was called cool program rule. And you pass in this lexer token function, and you pass in the lexbuff. And if this worked, then we will get out something of type cool program. How do I know that? We promised it on line 36. And a cool program is just a list of classes. So one of the first things I might do is say parsed successfully, how many classes did we get? And instead of result, I'm going to call this AST for abstract syntax tree so that it matches up with the class nodes. Do the parsing. All right. So let's see if this compiles. This stuff never compiles. Empty. Did I mean empty? I totally did. This may be my favorite feature of the OCaml type checker. Line 100, is it empty? The world may never know. Let's remake it. Cannot remove main.mli. Whenever you do an rm in a Makefile, right? So cannot find, do we not do this correctly? Make clean, make the whole thing. All right, this time it builds. So we still have our single class test. Probably this isn't going to work, but let's go try it out. Oh my gosh, it parsed successfully with one classes. Sure it did. Let's make a little two class here. This is class 1, which has x, which is an integer. And here we have class 2, which has y, which is an integer. And we will ask cool to lex those for us. And we will run main on two classes clx. Oh my gosh! Parse successfully with two classes. I mean, that looks really awesome. However, we are required not just to output the number of classes, but to actually spit out the abstract syntax tree in a serialized format. To output the AST is a list of classes, blah, blah, blah. So I'm going to do that now because it will also help us do debugging. Like right now, I don't know if we're getting the classes in the right order or what their contents are. But once I start trying to print them out, we'll see if we're doing it correctly. So now I need some handy printout functions to see how things are going. And one of the first things I'm going to do is try to find my output file name. And what I conceptually want to do is turn foo.clx into foo.clast. How do I do that in OCaml? Well, it turns out there's a file name standard library part of OCaml that can chop the extension from a file name. So we will do file name chop extension, and then just to add back in CLAST. And we don't need all of these parentheses. So there's our output file name. And I often call my file handles fout, but because I'm going to be referring to this one so often, I will just call it f. So now we spend quite a bit of time writing utility helper functions to see how to print this stuff out. And it says a cool AST is a list of classes, output the list of classes. To output a list, output the number of elements, then a new line, then output each element in turn. So here's how this sort of thing might go. So I have a output cool program, which takes an AST. And this is just output class list. Output class list when you give me an AST. The first thing we do is output the number of these. Right? And then for each one, we print it out. And we're going to use higher order functions. And we just use list iter, and we're done. I'm going to get tired of writing printf every time. So way up at the top, this is like import in Java. Right? I'm just going to import printf. And to output a class, what do? To output a class, output the name of the class as an identifier. All right. Well, at this point, we get a chance to see what this class actually looks like. And for us, there's only one choice, class no inherits. But maybe later we'll have more. So this is the class name and the class features. And it says output the name of the class as an identifier. So we will output the class name. And then it tells us to either output no inherits or inherits, and then the list of features. Well, for us, this is clearly the no inherits case. Oh. F printf, F, we are no inherits. And then it would tell us to output the list of features, but this is a lot of code, and I want to do just a little debugging. I want some intermediate testing to make sure that we're doing it correctly. So I'll just close this off with an in, and then what we would actually do is output the cool program with our AST, and then close F, and then we're done. And if this works correctly, we'll see the number of classes and then each one's name. Oh, forgot to output an identifier. Right? What's an identifier like for us? Remember, it's got the line number and then the string lexeme. How do I know that? Because I promised it to myself here. This was the string and then the other string, and I said I'd be lazy and use strings for everything. Let's get rid of that. So how do I output an identifier? To output an identifier, output the source line number, then a new line, then the identifier string, then a new line. Great. All right, let's see if this even compiles. Unbound value out class list. Did you mean output class list? Yes, I did. Output. Try again. Ah, my gosh, it works. All right, so we have our, was this it? Okay, this looks pretty good. One of the first things I'm going to do is parse this test.clx, but store the output in ref so that I can do a little bit of testing. And now we're going to run main on test.clx and see what's in test.clast. And it says 1, my test, no inherits. And let's see what the top of ref clast is. 1, my test, no inherits. Oh, look, everything we're doing correctly. We just haven't done the rest of it yet. Okay, I have gained confidence. All right. So now it's time to do the rest of it. To output a list of features. Well, how do we output a list? To output a list, output the number of elements, then a new line, then each element in turn. All right, can do. So number of elements. And then once again, we're just going to use list iter. Features. And now I need to tell you how to output a feature. And once again, these are, we've got this complicated maneuver here. There are multiple different types of features, but the one we have is attribute no initializer. And this is the attribute name and the type name in that order. So how do we output a feature? The name of the feature, and then a new line, and then any subparts as given below. And this is us. We output this thing. All right. So let me just say attribute no init new line, because we are required to do so. And then we say the name, and then we say the type. Let's even call these attribute name, attribute type. All right. Does this make? Line 127. Oh my gosh, what is this? These long error messages. Whenever you see format, this means you made a mistake with printf. Like there are too many arguments. You didn't pass in enough of them. All right, so line 27. Too many arguments to printf. Why are there too many arguments? Because we forgot the semicolon, so it thinks this whole thing is one line, so it thinks there are too many arguments to this fprintf. So we fix this by adding the semicolon. Make unbound value class features. Did you mean class features? I hope not. It's amazing that I can spell in English. Actually, it's not clear that I can spell in English. Features. Sure, there we go. All right, line 138. Identifier is string, string, expression. All right, let's just go see that. Attribute, no initializer. Oh, well, these are two identifiers. They're quite correct. An identifier is a string crosses string. And let's just go double check how it wants us to print these out. Output the name as an identifier and then output the type as an identifier. So rather than this little printf, what we want here is output identifier at her name and then output identifier at her type. All right. Does this build? Oh my gosh, it builds. All right. So now do a little testing. Here's our test.cl. Right. We'll remove the abstract syntax tree version just in case and run our thing on the Lexer version. And now we've got quite a bit. What did the reference look like? Oh, they look really similar. How similar? Oh my gosh, no differences. Hallelujah. Probably shouldn't clap in front of the microphone. All right. This seems pretty tempting. Actually, at this point, we might even pass a test case or two if there are any test cases on the server that are so simple that they're just one or two classes. So let's try that out. To submit something to the server, I need to make my little zip file. And for full credit, I need to include my MLY file. And I'm probably going to be doing this a lot. So I'll actually make a little rule for it. In my Makefile, I need to put in main.ml and main.mly. And to do this zipping, we need main.ml. And then when we're making things clean, we, of course, remove the zip file. Makefiles can have comments. Yours should. Should. Oh my gosh. Should. Yes. Double plus should. Oh, it's 1984-tastic. All right. So let's see if we can go make our zip file. And we added the ML and the MLY file. And now, somewhere over here in our submission server, we'll just reload. And we're going to choose a file. And we'll try ww6y. And this is for the parser. And we're submitting for just testing. Go, go, gadget. Big bucks and no whammies. Oh my gosh. We passed class with one field. Oh, class with two fields. Empty class, also known as class with zero fields. Two classes. Two classes with one field. Oh, but we're totally failing to class one inherits. You're right. We're totally failing that. Also, we're failing every single negative test case. We haven't even seen what happens on a parse error. But look, this is already pretty good. All right. So let's see what's supposed to happen on a parse error. Let's just take our two class example, and we'll make a bad example. No, not cat. Copy. And down here on line 4, I'm going to write the word class twice. And this is clearly illegal. Cool. So if I were to run cool and lex bad.cl, that's okay. But if I try to parse bad.cl lex, it's a kiss of death. Error for parser. All right. So what happens when I run our thing on bad CLX? All right, we're very close. We appear to be raising some sort of exception. But for full credit, we have to print out the line number where things are happening. So let's go back in here. And that exception, it turns out, is getting thrown right here where we're doing the parsing. Okay. So we could try to do this, but if there's any sort of exception, then what was this supposed to look like? Error for parser, parse error, except we don't know what line it's on yet. And then we're supposed to exit the program before we start making the output. So let's see if we can remake this. And now, when we run on our bad CLX, we're getting this error. This is pretty close to what we want, except that we don't know the line number. Don't know the line number. Well, conveniently, we thought ahead. What we're going to do is keep track of, and you might need something better than this, but this is totally going to work for now. We're going to have a last line number variable. Maybe we start on line 1. And down here, when we pull off the line number, the last line number gets the line number we just read. So that when it is time to print out an error, the line number we're going to blame is the one associated with the token the parser just asked for, the most recent token. Let's try it out. Ah! It correctly yells at line 4. Because that's where the bad token is. All right. I like this quite a bit. Let's actually make this zip file and see about resubmitting it. Maybe we'll get something better. It's unclear. Re-choose this file just in case. I never trust the form to actually re-update. All right. 2 fields. Oh, look. And now we are passing some negative test cases that are very simple, like a class with no name. That's basically the one we tried here. All right. And now we're going to do just a little bit more. We want to do some attributes, we want to do some attributes with initializers because we want to show off expressions. So, in addition to this feature, attribute no init, you can also have one that actually does have an initializer. Where did I get that? I've lost the cool reference manual. It's this part right here. This part right here, left arrow expression. Okay. So this would be an attribute with an initializer where we have all the same parts from before, but now we also have the initializer. And this means that I need some way of parsing cool expressions. Now, there are a billion, by which I mean like 20, cool expressions, all of these things in here. And we're going to do like this one to get you started. So one of them is expression plus expression. There's also expression times expression. And there's just integer. And we'll do those 3, and then you could put in a lot more. Right. So the real trick with expressions is that we're going to need to keep track of line numbers, right, potentially, pretty much everywhere. We'll see how that's working out. So up here, where we have feature, we also have attribute init of identifier times expression, and we need some way of doing an expression. And a common approach to this, misspelling, is you'd think, oh, well, I have my my plus of expression times expression, and I have minus, and I have integer of int, but can say string for us. But this is actually going to make it very difficult to track line numbers. We need to track line numbers everywhere. We could put in a little line number at the start of every one of these, but that gets old fast. So an approach commonly used is to call this something else, like the inner part of an expression, and say that a real expression is a line number followed by the inner part of an expression. So now it's like I've added this string line number field to each one of these, and then if I add a new one later, it gets this stuff for free. So string is the line number for every expression. So let's take our integer rule first. We know from integers that the first value that we get from the lexeme is the line number, and the second is the actual integer. So we've got the line and the integer text, and those are number one is just this first token. And we want to return a pair of the line number, and then notice this capitalization matters, right? These are integer expressions. In fact, just for convenience, I'll write E at the front of every one of them, just so we see it. Lost it, E integer, and we put the integer text in there. Okay. So now similarly for plus, we need to know where this lives, but once we have that, we can just do E plus of number 1 and number 3. And in fact, this is what a lot of our rules are going to look like. If we can figure out where this thing lives, then this is just E times of number 1 and number 3. So in a plus expression, what is its line number? Well, we go back to the not this. We totally go back to that. And commentary, video guides, what to turn in. We search for line number. Slowly. So slowly. All right. Oh my gosh, stop searching. All right. The line number for an expression is the line number of the first token. All right. So all I really have to do is figure out what the line number of number 1 is. Like if this were a field, I would just do something like this. But it's not a field, it's a tuple. Oh, isn't this slick? If you like, I can add parentheses around here to make this look a little better. All right. That underscore means I'm ignoring it. What this actually is, this is the inner exp on the left of the plus, but I don't care about it. I just care about the line number on the left. Okay. So now we've been reading all of these expressions in, and let's go see if this code even compiles. If it does compile, it's going to give us a warning that we're missing a case branch, but let's see how it works. All right, line 65, syntax error. All right. Oh, this colon is supposed to be a bar. Symbol left arrow is undefined. Huh. You're right. And also, I should add it in there. All right, 68, pattern expected. What did we forget? Expression number 1, pattern expected. Did I forget a semicolon somewhere? Attribute init. Sometimes OCaml really wants you to have extra parentheses everywhere. Let's see if this is one of those times. Nope. 68 characters, 34 to 35. Here's 68. Here's 34. It says pattern expected. All of our expressions should be returning these expressions nodes, which start with a string crossed with an expression inner. The string is the line number. I like all of this so far. Maybe I made some sort of typo here. One of the tricks that I will sometimes do in OCaml, if I'm having trouble debugging something, is that you can replace almost any expression with fail with, which just raises some sort of exception, and get it out of there. So we'll just remove a lot of this code for now. And this will let us see if we've made a mistake somewhere else. All right, so here it's saying this pattern matching is not exhaustive on line 161, and it's correct. For an attribute initializer, we have the attr name, the attr type, and the initializing expression. How do we print these things out? Well, we write attribute yes in it. And then once again, we output these identifiers, but now we need some function to output an expression for the initializing expression. So I guess we'll have to write that. And that's going to vary. Right. This is the line and the inner expression. I'm going to match the inner expression, and there are 3 choices. Plus, minus, and integer. Let's do integer first. how do we actually print out an integer? You print out the word integer and then the integer constant and then a new line. So something like that. How do we print out a plus? You write the word plus and then the two sub-expressions. So that looks something like this. We write the word plus, and then we output expression A, and then we output expression B. And similarly for minus, except we want to write out the word minus. See if this code compiles. 176, expression has type string. Oh, they're still right. Fprintf F. All right. Now this code compiles, but we're not actually building the right abstract syntax tree because up here we were running into some error that I couldn't quite figure out. And I thought when we were reading in these integer tokens that we had the line number and the integer string as number 1. And let's see if this compiles. We're going really slowly. Okay, it says, great, you didn't use the integer string. Well then, I get to return my line number and one of these e integers of the integer string. We're going to like this. All right, we like that. Getting closer. All right. And now for expression plus expression, the line number of first token, and then something else is number 1. And we're going to return the line number of the first token, followed by an e plus constructor of number 1 and number 3. You're going to be okay with that, OCaml? First toke, that would have a different meaning. All right, so this time it's okay. So I'm not sure exactly what the typo was before. But we can now do the same thing for times. And I'm just abbreviating because line number of first token is hard to spell. Now there's no constructor e times. Oh, you're right. Let's try again. Has no constructor e minus. You're right. The reason I'm doing plus and times instead of plus and minus is that I want to show off precedence and associativity. All right, this totally builds. So now let's make an initializer test. Oh my gosh, look at this cool expression. So I should be able to lex this. I should be able to parse this with the reference lexer. And now, what happens when we try it out ourselves? Well, we print out main no inherits an attribute with an initializer x gets 2 plus blah times. Well, let's see how this goes. We will diff bb our answer with the reference answer. And they don't look quite the same, but I can't quite see why. We are forgetting something very important. Take a look at this. Before every expression, the reference parser, which is on the right, is printing out the line number on which it occurs. We're forgetting to print out the line number. How would we know to do it? Output the line number of the expression and then a new line. We would read the manual, which I forgot to do. Oh, if only we'd gone to great lengths to keep the line number around. We've gone to great lengths to keep the line number around. Always output line number first. We remake it. We rerun main. We redo diff. Oh, and there are no differences at all. All right. So we could resubmit this. But let's actually take a look back at this. Back near the top, we had this precedence and associativity, right? Plus and times, which we copied from somebody else. But what if we'd forgotten those? What if I comment those out for a minute? Now when I rerun make, notice that it says for shift reduce conflicts. Shift reduce conflicts. That sounds bad. How do I go about figuring out what they are? Well, we need to ask ocamlyacc to generate the parsing tables and report on conflicts. We have to pass it -v. So we just add in this -v here. I won't leave a comment in Makefiles because that's asking for death. But now there's this main.output file. And you can search for conflict. And in class, we cover how to read these so-called parsing items, like the dot means here's where I am, and you can see, oh, sometimes in the dot I'm about to see a plus, and sometimes I'm about to see a times, or I could be done with a plus. But look, it tells you right here, one of your conflicts is between plus and times. You just read out these two lines. So that sort of thing would probably give me a hint that I need to include precedence for plus and times. It's not always that easy to figure out, but this particular time it was. All right. So let's just make sure we'll remake this. We will remake our zip, and we will resubmit, re-choose our file, resubmit for just testing. Okay, okay, okay. We still haven't done inheritance, so we're not getting any exciting cool class initializers, but this is what you do for programming assignment 3. You just increase your grammar and add more things as time goes by. All right, so what did we want to cover? OCaml and ocamlyacc did both deserialize the PA2 CLX file. Yes. Use the PA2 tokens as Alexer. Yes. Represent the AST. Define the parser via grammar rules, line numbers, and error handling. We did both. We serialized it and we submitted it. And now what I'm going to do is just go through, you can end the video at this point, but I'm going to go through everything in our submission so that you can take a look at it. This special %sign open curly brace is for putting OCaml type declarations. We opened printf to avoid typing it all the time. Identifiers, type, strings, we used the line number plus the lexeme. We left everything as strings rather than converting them to integers. One other reason for that is that OCaml uses 31-bit integers if you're not careful. Don't get that wrong. Our cool class, we only have no inherits, but there'd be an inherits version later. We have 2 features. There's actually a 3rd feature. You can declare a method. And then here's our expression type, and there would be many more of these. And we're using and over here because these types all depend on each other. Right? And then a cool program is just a list of classes. Here we start having our parsing rules. We ended with this special %sign curly brace maneuver. We declare all of our tokens, and for every token that has a line number, we put it here. And if a token has a line number and a string lexeme, then we put it down here. We also had our special end of file token. Declare our precedence and associativity. And then we indicate what our starting rule is. For us, it was a cool program rule. And because they use type inference, you have to give them the first type and then they infer all the rest. So you say what the type of this is. And for us, it's cool program. Cool program is a list of classes followed by an end of file. And class list, or indeed anything list, is either nothing or they're separated by semicolons. All right. Cool class, class keyword, type, lbrace, feature, rbrace, all that good stuff. Here's our feature list, and you just write down these rules. Where do we get these rules again? Here. Cool syntax. And we've got expressions, plus, minus, times, integer. We made up names for each of them. I have a special helper function to read in PA2 CLX and deserialize into OCaml tokens. This is what this is doing. All right. We're using a queue. We're being imperative about this. We get the line number, we get the token type, and then a few special tokens. We also get the lexeme. You'd have to add a bunch more to this. All right. We're storing the line number here so that we can always know it at all times, because that's a surprisingly big part of this assignment. We read in the token file name, we construct the tokens queue, we make a fake lex buff. We'll never actually read this string because instead we're always reading from this queue. We store the last line number as a global variable because we are shameless. And this is our function to pretend to be a lexer. This is our lexer that uses the PA2 tokens. All right. Return PA2 token to OCaml's PA3 parser. This is what we're doing here. And then we actually call our parser using the cool program rule. And it's just, the library says you pass in this function and then the lex buff first. If there's some sort of problem, they will raise an exception, at which point we print out where we think the error is. And if not, we have a lot of serialization code, and we're supposed to write to a file. And I have a bunch of recursive procedures that output class lists and classes and identifiers. To output a list, you output the size of the list, and then you do a list iter, blah, blah, blah. And we just write one of these for everything. One for classes, one for features, one for expressions. And some of them are very simple. You just print out one thing. And a lot of them will match on the abstract syntax tree we defined above. And then we're done. All right. Talk to you all later. Bye.